So welcome to my next webinar in the Modern Java by Example series. What we're going to do today is we're going to continue our discussion of the image stream gang program, focusing this time on how to implement it using various RxJava features. So with that, let me go ahead and share my screen, and we'll be off and running. So let's go ahead and start by taking a look at my Github repository. This is what we've been focusing on thus far, and there'll be no difference today. If you take a look here under the image stream gang folder, in the command line folder, zooming down into the main Java live lessons folder, you'll see there's a bunch of subfolders. The most interesting of which, of course, is the streams subfolder, and that is what contains the code we're going to look at right now. We're going to look at the image stream RxJava1.java file and the image stream RxJava2.java file. Those are the two things we're going to look at. So let's go ahead now and shift over to my IDE. Here is the code. If you recall, again, if you run the program, the RxJava1 and RxJava2 implementations we're about to look at both perform very, very well. So let's take a look and see how they're going to be implemented. As you can see here, this first implementation we're going to look at uses the flat map idiom that RxJava defines in order to be able to download, process, and store images concurrently. And under the hood, we also connect the RxJava mechanisms with Java's common fork join pool. And we're also going to use the ability to be able to grow and shrink that pool dynamically by using the managed blocker mechanism. So everything we're going to talk about today builds upon some of the discussions we've had in previous lessons. And so it's a good idea if you want some basis and grounding for this discussion, go back and watch some of the preceding videos that I've done where I talk about the overall application for image stream gang, the sequential and parallel streams version, the various completable future versions, and that will then set us up nicely to compare and contrast that with today's RxJava versions. So let's go ahead and take a look here. Here's the main method we're going to look at. This is the process stream method. This is called automatically by the image stream gang framework, which is what drives all these different examples of Java concurrency and parallelism mechanisms. All right, so what we start out doing, again, as always, is we go ahead and get the input. And the input here is essentially a list of URLs. And the first thing we're going to do is we're going to use a factory method defined on the RxJava observable in order to convert the URLs in that input list into a stream of observables. So if you're familiar with RxJava, you know that observable is kind of the root of a lot of stuff there, although we'll see later there's some other kind of parallel concepts such as flowables and parallel flowables we'll talk about shortly. And so from iterables takes, in this case, something that's an iterable, a list, and converts it into this stream of observables. And that's one of the cool things about RxJava's observables is they can have 0, 1, or many elements in them. So it gives us sort of a common way of treating what could be multi-sized inputs in a common, consistent way. So after we got this stream of observables, we then go ahead and convert them by downloading and filtering them in parallel using the concurrency mechanisms that are available in RxJava. Now, the features that are available here that we're going to talk about are some of the ones that have been around for a while. This is the so-called flat map concurrency idiom. Later, we're going to look at the parallel flowable idiom and the constructs that are defined to do that. And you'll see that there's basically pros and cons. So how does this work? Well, we take this stream of URLs, the stream of observable URLs, and for every URL in the stream, we go ahead and use the observable just method. So for every URL, we're going to go ahead and say, please emit one observable for just that URL, one, of course, at a time. And then what we do is we're going to use this super cool compose method. And this is a method that's used to allow extensibility within RxJava. You can sort of define your own kind of operators, if you will. And to do this, we're going to use something called RxUtils Common Pool Observable. And let's go see if we can click on down and look at this. And there it is. This is the common pool observable in my RxUtils class. I defined this class. This is something I found myself using over and over again, so I made it a little reusable class, and then I can use it in all my projects. And what this particular implementation does is it takes the observable and it subscribes the flow related to this particular observable using the common fork join pool. So we're going to use the common fork join pool as the scheduler that we're going to subscribe on. Okay, so we'll kind of pop back out here and come back and talk about this later. So what's going to happen now is this particular flow, starting from observable just and continuing down to the bottom of this flow, are going to run in their own task. Each of these observables, each of these URL observables is going to run in its own task in the common fork join pool. And of course, that uses the underlying Java fork join framework, which does lots of cool stuff. At some point, I'll give a tutorial where we'll talk more about that explicitly. The next thing we're going to do is we're going to use the filter method on observable in order to get rid of anything that has already been cached locally. So if something has been cached, and that's this URL cached method, which returns a Boolean, if it has been cached, we want to ignore it because we're going to ignore cached images. That's just the semantics of this particular program. So we're going to go ahead and essentially winnow out or filter out images that have already been cached. So the particular way of doing that here is we say URL cached, LURL, then we negate that, and if it's not cached, we're going to let it go through. Notice this also shows off another kind of interesting thing about the way that RxJava works. We have to rename this thing because if we don't, we already have a URL defined here. And if we called this URL here again, we'd have a conflict. So we're going to call it LURL for local URL. But same basic, it's the same thing. So we go ahead and only let non-cached images flow through the filter. And the next thing we do is we go ahead and we apply the blocking download call. Now, I'm not showing you URL cache because I already looked at that yesterday and I think the day before. So it's the same code. Under the hood, this particular code uses, I think it's actually Java streams. I should probably, if I was really being consistently RxJava-esque, I would rewrite that using RxJava. That's probably a good extension for the future. But it also demonstrates that there's no problem mixing Java streams code with RxJava code. It's just Java bytecode when all is said and done. So we now have, at this point, only non-cached images to consider. And so we're going to go ahead and download them using the blocking download method reference. So if we peek down here, you can see here's blocking download. Blocking download is going to use the blocking task call and manage block method to download the image. And again, this is something we've looked at before. Blocking task call and manage block is just a nice little wrapper around the Java fork join, common fork join pool in order to be able to make it expand itself automatically when blocking operations are called. So what we're then going to do, the blocking download is going to convert this URL into an image, and then we're going to go ahead and pass that to flat map with apply filters. This should all look very familiar to you by now. This looks very much like what we've done in the past. In fact, this code looks almost identical to the equivalent Java parallel streams code. The only difference really being that instead of saying kind of, parallel stream, we say compose, and then we integrate this with a common fork join pool. But other than that, it looks suspiciously much like the earlier code. So let's go ahead and take a look at apply filters. And apply filters is kind of interesting. Let's go look at that. So here's apply filters. Apply filters is now code that we custom wrote for RxJava. What we're going to do is we're going to take the image that was passed in here, and then we're going to take the observable from iterables factory method, and we're going to have it emit all the filter objects. So if you recall, mFilters is basically the list of filters we want to apply to every image. And what we're going to do here is we're going to get this list of filters turned into basically a stream of filters. And then for every filter, we're also in parallel using the same flat map idiom for concurrency that we did earlier, except earlier we were doing this for downloading images. Now we're using it for filtering and storing the images or transforming them. We're going to go ahead and take each filter, emit it. We're going to run that in the common fork join pool. So once again, we're going to connect it together with the common fork join pool using the compose method and RxUtils common pool observable, just like we did before. So it's identical. And then the last thing we're going to do here is we're going to use the map call to go ahead and map that filter and call the make filter decorator with image method, connecting the image with the filter. So again, this really looks quite a bit like the parallel streams code. If you want to have some fun, I recommend going back and looking at the two code bases side by side. They look almost identical in a lot of ways, even though the underlying mechanisms are, of course, quite different, because one is parallel streams, and this one, of course, is RxJava. So what we get back from this is an observable of images. And of course, an observable can have multiple elements in it, which it does, one for every filter that we just went ahead and applied. So what's going to happen here is all of this code is going to run concurrently. Each of these different URLs will be processed concurrently by different threads in the common fork join pool. And we're also then going to apply the filters in parallel as well. Again, very much like parallel streams. So then what we're going to do, we're going to have basically this observable, all these observables coming back through this stuff. And flat map, of course, is going to make this be a single stream of images that are going to come out of this call to flat map. So flat map will make sure that everything's at kind of at one level rather than being nested observables. So we're going to have just a stream of observables to images come through. And then what we're going to do is we're going to, again, apply a technique very much like Java streams and parallel streams with their collectors. We're going to go ahead and reduce with, and we're going to give it a constructor reference to the collection we want to reduce into. And then we're going to go ahead and give it a method reference to a local method we wrote called append. So let's go ahead and take a look at append. So if you go down here and you take a look at append, you see what append does is it's going to take a list and a new item. It's going to add the new item to the end of the list, and it's going to return the list. And this is just a way of adding something at the end of the list. Sadly, there is no append method in Java out of the box, so we had to write one ourselves. Kind of weird they don't have that, but it's very useful. So the last thing we're going to do, we're now going to end up basically with an array, or rather a list, implemented as an array list of images that we've downloaded and transformed in parallel. And then we're going to have our good friend blocking subscribe sitting here, and blocking subscribe will then go ahead and take this list of filtered images and just indicate how many of them were downloaded and filtered. So we'll go ahead and print that code out. So that's basically it. So again, it's really fun to go back and compare and contrast this implementation with the parallel streams version. I think you'll probably agree if you do that, that this implementation looks a lot more like parallel streams than it did the completable futures version. And if you look at the completable futures version of all this, which we looked at yesterday, it's actually, I think, a little bit more complicated than the RxJava version in some ways. And so this looks more like parallel streams. But the good news is the RxJava version performs more like completable futures. And we'll see that as soon as we get done analyzing the second of these examples today, these RxJava examples. Okay, so that was the first piece of code I wanted to walk through. I think you'll agree it's pretty concise, and in a minute we'll see how well it runs. Now let's pop over to ImageStream RxJava 2. And this particular implementation is going to use observables. Sorry, it's going to use RxJava, but it's not going to use observables. Instead, it's going to use flowables and parallel flowables. And parallel flowables were a capability that was added in RxJava 2, and they're more limited than observables, but they also are pretty easy to use with respect to parallel processing. And I'll just give you a kind of a taste of it as I used it for this code. So once again, the main method we're going to look at here is the process stream method. We get the input, which is the list of URLs, just like we did before. We convert that into a flowable of URLs. And you'll see here we have flowable. Before we had observable, just to compare and contrast this. So here's the other code. Here's observable from URLs. And the only difference here is now we have flowable from iterable, which gets it from the URLs. So very similar, but one is observables, one is flowables. There's two main things you can do with flowables. One, you can make them run in parallel very easily, as we'll see in a second. And then the second thing you can do with flowables is you can also exert back pressure on them. This particular example is not going to illustrate the back pressure feature because we're not worried about that, but it's another interesting aspect of flowables, and it's really why they were added, because they give you additional capabilities that you don't get with observables. But that's a topic for another tutorial. All right, so we take this stream of flowables, and then for each of them, we go ahead and use the dot parallel operator. The dot parallel operator converts a flowable into a parallel flowable. And then what we're going to do is we're going to compose this with the RxUtil's common pool parallel flowable factory method. And so let's go take a look at what that does. So if you go over here, you'll see that common pool parallel flowable will go ahead and take this, and I guess I should actually call this flowable because it's not an observable, it's a flowable. That was a cut and paste error. And what it says is, it says, please run this flowable on this scheduler. And this scheduler, as with previous examples, will be the common fork join pool that we get from Java JDK. Okay, so that's where we get that particular piece of code. So let's pop back over here. That's what we're composing with. So we're going to have parallel composition. And that means everything from here down to the point where we join it back together again to be a single flow is all going to run in parallel. So for each URL in parallel, we're then going to go ahead and filter the URL. That's exactly what we had before. We're going to go ahead and use the map operation to do the blocking download in parallel. And that's exactly what we had before. Just to make this clear, look at this code from before. Here was the code we had before. Notice we used the common pool observable before because we had an observable, and we used flat map. And now what we're going to do is the same thing. We're going to do filter, we're going to do map, we're going to do flat map. So if you go over here and look at RxJava 2, we do filter, we do map, we do flat map. The implementation is slightly different under the hood, as we'll see in a moment, but it's very much the same flow of behavior with our flowable. So let's go ahead and pop down here to apply filters. So this is the parallel flowable version of all this. So in this case, we're going to take flowable and say from iterable, which will go ahead and create basically a stream of these filter objects, one for every filter we want to apply to the image we're processing here. As with before, we say dot parallel to make it run as a parallel flowable. We then compose with common pool parallel flowable. This should start to look very similar because it's the same pattern. And then for each of these different URLs that we've got, or sorry, each of these different filters we have, we go ahead and for each filter, we're going to go ahead and map the filter to the decorator with the image. And so that will, again, in parallel, run all those things to apply the image transform, to filter the image, and then store it. Now, the last thing we do here is we use the dot sequential operation. And dot sequential is basically like kind of a join, and it goes ahead and merges the parallel flow back into a sequential flow. And that's what we get as the result of this. We get a sequential flow of all the things that were just processed in parallel. So if we pop back up here, you can see we've got this flat map operation, which is going to go ahead and end up creating a flowable of processed and stored images, or transformed or filtered images. So those things come back. Keep in mind they're still coming back. Keep in mind the way they're coming back. This is flat map operation that's called on the parallel flowable. So then again, we have to use the dot sequential operation, and the dot sequential operation, once again, will merge all the results back into a single flow. And then what we do is we take that single flow of all the processed and stored images, and this time, instead of using reduce with, we're going to use collect into. So collect into is very much like reduce with. I'm honestly not sure why they have two of them, but they must differ somehow. And what we do here is we make a new array list. You can't use a constructor reference here. You have to actually make an object this time. So we make a new array list, and then we pass in the add method. And what collect into does, of course, is it just takes each element in the flow and it adds it to the collection that we put there. As with the other implementation, we add blocking subscribe here. I'm just using blocking subscribe so that we don't fall off the end of the program while it's running. And as before, when everything's finished, because blocking subscribe kind of sets the wheels in motion, then filtered images come back and we say filtered images.size. So you can see kind of how this all works. And it, again, is just very, very similar to the example we used earlier, except that before we used reduce with on observables, and now we're using collect into using flowables. And I could have swapped those around. I could have reduced with flowables. I could have collected using observables. That doesn't really make any difference. Just using two different sort of joining mechanisms, if you will, to kind of gather everything back together. So this is kind of a scatter gather like model using parallel processing. So that's basically what I wanted to show. Let me go ahead and see if I can run this code now. I don't see any reason for it not to work, but you never know when you're doing a live demo what strange gremlins may befall you. So it's compiling and looks like it's going to start running. This is running all the different tests. So it's running sequential stream, parallel stream, the two completable future implementations we looked at yesterday, as well as the two RxJava implementations we looked at today. And if I was to run this test, 20 times, I'd get slightly different results probably. But in general, the completable futures runs very well. The RxJava stuff runs very well. As you can see in this particular case, completable futures 1 for everything. Let's just for kicks, let's go ahead and run it again and see if we get the same results this time. Because I'm running this live over my home network, and there's sometimes congestion because everybody in our neighborhood is doing Zoom meetings or homeschooling or online schooling or whatnot, we may get a little perturbation each time. So you can see this time, completable futures still tend to dominate for the big files, but in this case, the RxJava implementations kind of moved up a bit and did better for the smaller files. I think we're in the noise ratio, these differences are so minuscule that it doesn't really matter. But it's worth noting that, of course, all these parallel and concurrent implementations perform better than sequential streams. That should come as no surprise. Parallel streams obviously does better than sequential streams, but parallel streams does not typically do as well as either completable futures or RxJava. And I've found those results to be pretty consistent across the different tests I've done. Typically, completable futures is almost always the fastest. RxJava typically comes in second, sometimes first, depending on how things go. And then parallel streams works better, but isn't quite as good. And it's actually kind of interesting looking at the large files. That's the first set of results up here. You can see that it took about 2,400 milliseconds to do this sequentially for all the images we downloaded and processed. And with completable futures, it took basically about a quarter of the time, give or take. And this is actually a quad core machine, so we're getting pretty much linear speed up there, which is good. You'll see that parallel streams don't run quite as well. They're probably about, instead of a quarter of the time, it's about a third of the time to run, give or take. And so there's just more overhead. I think probably the main difference there is that everything in parallel streams is running synchronously, whereas everything in completable futures is running asynchronously. And I think RxJava is a little closer to the completable futures execution model, even though the source code itself looks very much like the implementation for parallel streams. So I thought you might find that all interesting. I certainly found it was quite interesting. What I'd like to do now is kind of go ahead and give you a preview of coming attractions. So what we'll do next time we get together is we'll explore some new examples. I have had lots of fun putting some other stuff together recently. And let's go ahead and shut everything down here. There we go. So this is another example. This is probably one that we'll take a look at either tomorrow, Thursday, or Friday. Still, the jury's still out as to which one I'm going to do next. But basically, this particular approach is just a tour de force of all kinds of crazy completable futures mechanisms. And I came up with a really cool little testing framework to demonstrate how to run everything at full blast speed without having to worry about the program exiting before all the asynchronous computations are done, So we'll definitely cover that in the not too distant future. And then let's see if I can find the other example. I also wrote another cool RxJava example. And let's go ahead and find that. It's lurking down here somewhere. Let's see. It is in the RxJava folder, and it's EX5. There's a little README file in all these folders that kind of give you an overview of what's covered there. So you don't have to try to remember the numbers, but it'll explain what's there. And this is a really cool example of maybe a week or so ago, we had looked at an example of a web crawler that used completable futures to crawl a recursively defined directory structure, either one that is on your local machine or one that's accessible over the network using the World Wide Web. And it would go and crawl all these folders up to some max depth that you could define. And it would do this all concurrently using completable futures. And it would count the number of images that were available on a given page. I rewrote that program. So we're going to get a chance to look at how to do that implementation using the RxJava implementation. And so that's somewhere in here. I think this is actually a different example, but it's also one that we'll look at. Let's see if I can find the other one. That might be EX4. I've been having lots of fun lately playing around with all this stuff and teaching myself RxJava on the fly and then doing these tutorials. So I have lots and lots and lots of stuff. Let's go ahead and take a look. The README file. So, yep, here we go. So it's in RX4. So this is the README file that explains what we've actually got here in each of these files. So you can see EX4 is the one that has the version of the recursive web crawler that's really cool. So let's go ahead and take a quick look at that. I'm not going to go through it today. I'm just going to kind of give you a preview of coming attractions, and then we'll talk about those later in the week. So if we go in here and we look at RxJava, EX4, this is an RxJava implementation of this recursive web crawler. And it's interesting because it does exactly the same thing, but it does it using RxJava features as opposed to using the completable future features. So we'll take a closer look at this later, but basically what it's going to do is it's going to let us recursively traverse these hierarchies and do cool stuff with them. And then the other thing I was starting to show you before is this example that is another variation on an earlier program that I showed. And this earlier program I showed maybe a week or so ago demonstrated how to do timeouts with completable futures. So we had a completable future timeout mechanism. And this EX5 program re-implements timeouts, except this time we're going to use RxJava to do the timeouts. And it's really fun to compare and contrast the difference between the RxJava timeouts and the completable future timeouts. They both integrate timeouts. They both do essentially the same thing semantically. And then I'll let you decide which variant you prefer, whether you like the RxJava way of dealing with timeouts or whether you like the completable future way of dealing with timeouts. So those are other topics that we're going to be talking about in the coming few days. So with that, let me go ahead and shift back over here and just remind you where you can find all the stuff that we're talking about. So here's my website. You can go and look at the live lessons folder, and then we have the RxJava material that we've been talking about with all the examples spelled out. And then there's also my Java 8 folder, and there's lots of fun, cool things in the Java 8 folder, which is also explained here. And then there's also plenty of other examples that you might want to poke around with. So don't be shy, take a look at this stuff. Also, feel free to go to my Facebook page and subscribe to the various Facebook groups that talk about Java concurrency and patterns, and I post lots of other interesting things on those pages. So again, I really appreciate everybody taking time to come and learn what we've been covering here in these tutorials. Everything gets uploaded to my website, so take a look at my YouTube channel, which is entitled Modern Java by Example. And if you like this content, don't forget to subscribe. So thank you very much, and I'll look forward to seeing you again soon.